Hello and welcome to the second video on Equilibria. So what we're going to be talking about in this video is we're going to be talking about how we describe how the temperature, concentration, pressure and catalysts and how altering those different conditions can affect equilibrium. Now what I'm going to do is I'm going to describe sort of the generic definitions of the changes that we can do in those conditions and what effect they have. But I'm also going to do it using an example. And the example that I'm going to do it with is known as the Born-Haber process, which is the process of taking nitrogen and hydrogen gas and turning it into ammonia gas. Okay, so these are all gases here. So, first off, okay, just a little recap of what we talked about in the last video. Okay, we talked about the fact that we have these reversible reactions, and we have this concept of dynamic equilibrium, which happens in a closed system, whereby we have the forwards and reverse reaction happening at the same rate. Okay, now I did talk about those couple of terminologies. We talked about the forward reaction being this one, and we also talked about the reverse reaction being this one. A couple of other things that we need to be able to talk about so that we can describe how these affect the equilibrium is we talk about the position of the equilibrium. Now the position of the equilibrium is just where the equilibrium lies between the products and the reactants. Now to help us describe that, we also talk about the left-hand side of the reaction, okay, or left-hand side, and we also talk about the right-hand side here of our equation. Now, whenever you've got a question that involves conditions, you will also get what's called the enthalpy change of the reaction, okay, which is the delta H. Now, I'm going to talk about enthalpy in a completely different module, but for the moment, all we need to worry about is whether it's exo or endothermic. Now, in this case, it's endothermic. Now, okay, what reaction does this associate with? Well, this associates with the forward reaction. So the information that you're given will always associate to the forward reaction. So what that means is when we react nitrogen and hydrogen together to form ammonia, it's an endothermic reaction, i.e. it gets colder. So that's some of the terminology that we're going to be using to describe how changing some of these conditions affects the position of equilibrium. So let's start with temperature. For all of these, there's a principle known as the Chateliers Principle, which says that essentially, whenever a change to the conditions of a reaction that's in dynamic equilibrium is made, the reaction will shift to counteract that change. So, if I was to take temperature as an example, if I was to increase the temperature, what this reaction is going to want to do is it's going to want to counter that change. So it's going to want to cool everything down. So it will shift to the direction that does that. So when we think about temperature, if we increase the temperature, what will happen is that the equilibrium will shift, this is an important word, to the endothermic direction. Or endothermic side, I'm going to call it. If we were to decrease the temperature, it's going to shift to the exothermic side because it's going to want to make it hotter. Okay, so let's look a little bit at our example, okay, up here. So we've got these definitions. If we were to increase the temperature, the equilibrium is going to shift to the endothermic side. Okay, so if we increase the temperature, okay, so our temperature is going up, okay, having an increase, it's going to shift to the endothermic direction. Now we know that the endothermic reaction is the forward reaction. So what's going to happen is the forward reaction will be favoured. Okay, so therefore the equilibrium shifts to the right-hand side. Now what this will do is it will increase what we call the yield of ammonia. Okay, so that's a good thing. Now, if we were to decrease the temperature, what's going to happen is that the reverse reaction is going to be favoured. Okay, so let's speed this up. So therefore, the equilibrium shifts to the left-hand side, and this will decrease the yield of ammonia. Okay, so in summary, increasing the temperature in this reaction will favour the forward reaction, therefore equilibrium shifts to the right-hand side, increasing the yield of ammonia. And the yield is just simply how much is made. Okay, so that's temperature. What about concentration? Okay, put a little line across here. Okay, so concentration. Again, Le Chateliers principle is applied. So let's think about what's going to happen. So if you increase the concentration of something, the equilibrium will shift to lower that concentration. Okay, if we were to decrease the concentration of something, the equilibrium will shift to increase that concentration. Okay, so let's use our example. So in our example, we've got nitrogen, hydrogen, and ammonia. So we're just going to pick one of those. So let's say we increase the amount of nitrogen. So we're increasing the N2 concentration. So what's going to happen? Well, in this case, the forward reaction will be favoured, because if the forward reaction is favoured, this excess nitrogen will be turned into ammonia. So therefore, we can say that the equilibrium shifts to the right, or to the right-hand side, which means that it increases the yield of ammonia. So let's think about the opposite. If I was to decrease the concentration of nitrogen, what would happen is that the reverse reaction would be favoured, and our ammonia would be broken up into nitrogen and hydrogen to increase that concentration of nitrogen. So the last one that we've got to think about is, when it comes to conditions, really, is all about pressure. So pressure is to do with moles of a gas. Again, applying Le Chateliers principle, if we're to increase the pressure, the reaction is going to want to alter or favour the direction that reduces the pressure. So it would create less particles of a gas. So if we were to describe this as a box that we have some reactants in and some products in, and I was to increase the pressure, i.e. make the box smaller, what the reaction will want to do is it will want to turn it to the side that has a fewer number of particles, okay, because that will lower the pressure down. So when it comes to defining the effect of pressure, if I was to increase the pressure, the equilibrium will shift to the side with fewer moles of a gas. And again, if I was to decrease the pressure, the equilibrium will shift to the side with greater moles of a gas. Okay, now let's look at our example. So let's say I increase the pressure. Let's have a look. So how do we know how many moles of a gas there are? Well, if we look on the left-hand side of the reaction, we just look at the big numbers in front of things. There's no number, that's a 1. Okay, and we count up the numbers. So we've got 1, 2, 3, 4. So we've got 4 moles on this side. On this side, we've just got 2 moles. Okay, so when we come back to our little explanation down here, if we increase the pressure, it's going to go to the side with fewer moles of gas, which is the right-hand side. So therefore, if we increase the pressure, the forward reaction will be favoured. And equilibrium will shift to the right-hand side, increasing the yield of ammonia. And conversely, if I was to decrease the pressure, the reverse reaction would be favoured and the equilibrium would shift to the left-hand side, decreasing the yield of ammonia. Okay, so what about our last one? What about this one here? Catalysts. Okay, well, a catalyst, okay, does not affect the equilibrium. Okay, doesn't affect that position, doesn't shift anything to the left, doesn't shift anything to the right. What it does affect is it speeds up how fast the reaction reaches equilibrium. Okay, but it doesn't affect that position. Okay, so it only speeds up how quickly that equilibrium is reached. So how is all this information actually that useful? Okay, well, what we can do is we can use this information to identify what the best conditions are for the reaction. So if we're thinking about the purpose of this reaction is to get lots of ammonia, okay, that is the purpose of the reaction. We want to produce lots of ammonia. So we're looking for all of the ones that increase the yield of ammonia, okay, which is these 3 here. So what we can conclude from this sort of batch of information that we've just theoretically worked out, okay, is that we want a high temperature, okay, we want excess nitrogen and hydrogen, because if we've got lots of those, it will shift the equilibrium to the right. And what we need is we need a high pressure. Now, one of the things that we've got to bear in mind is a compromise, okay, between these different things. Because if we think about temperature, and when we have high temperatures or low temperatures, we need to be considerate of the rate of reaction. So we can have a high temperature to a point at which it either requires too much energy for not enough increase in yield, or it just doesn't really have an effect on the rate. So it just doesn't make a lot of difference. There's no point in doing it. Same thing for the pressure. High pressures are brilliant. They might make the reaction happen really fast, but at a point, it'll become too expensive for that reaction to occur. But I'll summarize that a little bit in the questions that I'll talk about in the next video. Okay, so a little bit of a summary. What we've talked about in this video is we've talked about the factors that affect equilibrium. Okay, we've talked about the temperature, the concentration, the pressure and catalysts, and how altering those conditions can change the position of equilibrium. Okay, we've talked about keywords like shift. Okay, we've talked about forward, reverse, we've talked about the left-hand side of the reaction, we've talked about the right-hand side of the reaction, and we've talked through an example using the Born-Haber process. Okay? So, thank you very much for watching. I've been Sensei Science, and as always, I'll catch you in the next video.